Think about it. Every single day, industrial plants all over the world are churning out just immense amounts of smoke. But have you ever stopped to wonder how we keep all that soot and ash from completely overwhelming our skies? Well, the answer isn't some kind of giant coffee filter. Nope, it's something way, way cleverer. Something that uses a little bit of what you might call static magic. Okay, let's get into it. So here's the big question, right? We're talking about millions and millions of cubic feet of hot gas moving super fast, and it's absolutely packed with tiny, tiny particles. How on earth do you clean all of that? Not just once, but continuously, 24/7. You see, the real problem is just how incredibly tiny these particles are. It doesn't matter if it's fly ash from a power plant or fine dust from a cement kiln. The exhaust is just full of these microscopic specks. They're so small in light that any kind of normal screen or filter, it would either clog up in seconds or the particles would just sail right on through. So to tackle this really stubborn problem, engineers turned to one of the most basic forces in physics, static electricity. And the device they came up with is called an electrostatic precipitator, or an ESP for short. And let me tell you, it was an absolute game changer for controlling air pollution. So what is an ESP, really? Well, at its core, it's a machine that uses these invisible electrical forces to literally pull the unwanted particles right out of the air. It's not trying to physically block them. It's grabbing them with electricity. And this is the perfect way to think about it. Seriously, if you've ever rubbed a balloon on your hair and then watched it magically stick to a wall, you've already seen the basic principle of an ESP at work. You've given that balloon an electrical charge, and that charge makes it attract to another surface. The ESP just does that on a massive industrial scale. To really get how this works, let's follow a single, lonely speck of dust as it takes a trip through one of these machines. Now, this whole journey happens in the blink of an eye, but it involves 3 very clear, very distinct steps. It's like a little 3-act play for every single particle. First, you have to give that particle a static charge. That's the rubbing the balloon on your hair part. Second, you use an opposite charge to attract it and trap it on a surface. And finally, you have to collect all that trapped dust so you can get rid of it. Charge, attract, collect. Let's see how the machine actually pulls this off. Okay, so this diagram shows us what's happening on the inside. As the dirty smoke flows in from one side, it's about to go through that 3-step process we just talked about. Charge, attract, and collect. First up, charge. The smoke has to pass by these high-voltage wires. These things create a powerful electrical field. It's called a corona that literally zaps every particle passing by, giving it a negative charge. Second, attract. Now that all those little particles are negatively charged, they are immediately pulled towards these huge collector plates, which are set up with an opposite, positive charge. They just stick like tiny little magnets. And finally, collect. Every so often, the whole system gives these plates a really good shake, a process called wrapping, and all that caked-on dust falls straight down into a big hopper at the bottom to be hauled away. The result? Much, much cleaner gas flowing out the other side. So that sounds pretty perfect, right? But, in the real world, things are never quite that simple. Engineers have to deal with a couple of sneaky problems that can make these ESPs a little less efficient. So here are the 2 big hiccups. First, you've got something called sneakage. About 5 to 10% of the gas can actually find a way to sneak around the main charging areas, especially near the top and bottom of the chamber. And second, there's reentrainment. When they wrap the plates to knock the dust off? Well, that shaking can actually kick about 12% of that dust back up into the air, letting it escape with the clean gas. Now, to handle all the different kinds of dust and different industrial gases out there, engineers realized pretty quickly that one size does not fit all. So they developed a whole family of different ESP designs, each one tailored for a specific job. The 2 most common types look pretty similar, but they've got some key differences. On the left, you've got the classic plate wire ESP. This is the industry workhorse, It's perfect for handling the gigantic volumes of gas you'd see at a power plant. Then you have the flat plate design, which uses a slightly different arrangement that makes it better at capturing certain kinds of really stubborn, hard-to-collect dust. And then things get even more specialized. There are tubular ESPs, which are basically a big honeycomb of pipes. They're awesome for dealing with wet or sticky gunk, or even hazardous materials, because they don't let anything leak out. And then you have wet ESPs, which are a super clever fix for that reentrainment problem. Instead of shaking the plates, they just constantly wash them with water. No shaking means no dust puffs. Okay, so we've seen all the complex engineering, the different designs, but you gotta ask, right? How effective is all this really? What kind of impact does this static magic actually have in the real world? This number, well, it kind of says it all. When an electrostatic precipitator is designed correctly for a specific job, it can capture up to 99.9% of the particles flowing through it. That is just an absolutely incredible level of efficiency. We're talking about turning thick, black, dirty smoke into almost completely clear gas. So while you'll probably never see one of these massive machines up close, they are out there, running 24/7 at power plants, steel mills, and factories all over the globe. They're a critical and often totally invisible line of defense that helps protect the quality of the air that we all breathe. It's really just a powerful reminder that sometimes the best solutions to our biggest problems aren't about brute force. They're about the clever, elegant application of an invisible force of nature. It really makes you wonder, doesn't it? What other invisible problems could we solve if we just apply the right bit of clever physics?